Section 10.3, estimating a difference between two means. In the first section of this chapter, we learned how to create a confidence interval for the difference of two proportions, P1 and P2. And in this section, we'll be covering the same thing, but instead of proportions, they'll be means. So we have mu1 and mu2. Again, we're going to have two different populations, and we'll be taking a sample from each of them. And we'll get sample statistics x bar 1 and x bar 2. We'll find the difference between these two statistics, and we'll use that as the point estimate of our confidence interval. Now, before we make the interval, let's talk about what the sampling distribution of the differences in these x bars will look like. So to refresh on what a sampling distribution is, we'll take these two samples and we get a difference between x bar 1 and x bar 2, but that's going to change with every set of samples we take. So when we're talking about a sampling distribution, we imagine taking samples such as these over and over again, always finding the difference and then make a histogram of those differences. So if we were to do that, we would find that the shape is approximately normal as long as we have a sample size that's greater than 30, or the population distributions are approximately normal. The mean of the sampling distribution is just going to be whatever mean we see in our sample statistics, or the difference of the means in our sample statistics. And the standard deviation is going to be given by the square root of sigma squared over n plus sigma squared over n for each individual sample. Just like last chapter, there are some conditions that need to be met for us to create this confidence interval, and they're the ones we're used to. We need to have a random sample from both of our populations, and we need to have a large enough sample, meaning that either the sample size is greater than 30, or it tells us that the population distribution is approximately normal. Or if neither of those two things are met, we would look at the actual sample data and see, does it look approximately normal in a histogram or a dot plot, etc. Now, the form for writing this confidence interval is really similar to what we did in the first section. We're going to start off by just subtracting our two x bars. That's going to be our estimate for mu1 and mu2. That will be called our point estimate. And then we're going to add and subtract a margin of error. And that margin of error is going to be a critical value times the standard error. Now, the standard deviation of this sampling distribution would be sigma squared over n for each sample. Add them together and square root it. But we don't know what sigma is. That's the standard deviation of the whole population. We only know the standard deviation of our sample. So we're using S in its place. And because of that, we'll have to use a t-score instead of a z-score. So here's our equation with all the variables filled in. We have the difference of our two sample statistics. That's our point estimate. And then after that plus minus, we have the margin of error. We have a t-score instead of a z-score. That's just going to be based on whatever confidence level we have. And then the standard error, s squared over n. We'll need degrees of freedom for this because we're working with a t-score. And since we have two samples, we'd find n minus 1 for both. And we're going to use whichever one of those is smaller. That's going to result in a wider interval. Smaller degrees of freedom means we have more variation, a wider interval. That's the conservative estimate. All right, so we'll pick which either of those is less. In our example problem, Ashton and Olivia wanted to know if generic chocolate chip cookies have as many chocolate chips as brand name chocolate chip cookies. They take a sample of 10 of each. We have Chips Ahoy and then Great Value cookies. They count the chips in each number of cookies here, and we're going to make a 99% confidence interval for the difference in the mean number of chips in these two brands. So to start, we'll check our conditions. We have random samples of both Chips Ahoy and Great Value cookies. And as for the large enough sample, our sample size is not greater than 30, and it doesn't mention anything about the population distributions being approximately normal. So we're going to take that data that it gave us in the lists on the previous slide, and we'll make box plots out of those. We don't see any obvious skews or outliers, so because of that, we'll say this condition is met. Now, with those conditions met, we can go ahead and calculate the sample statistics. So we would put this into something like Stapplet to get a mean and standard deviation for each of these samples. Next up, we'll go ahead and find our critical t-score for this problem. We need a degrees of freedom. In this case, both the sample sizes are the same, but if one sample size was larger than the other, let's say that this one had been 12, we would use the smaller of the two. So we have 10 minus 1, 9 degrees of freedom. We looked that up in the green table. We'd cross the 9 degrees of freedom with 99% confidence interval, or 0.005 one tail. All right, the two tails together would make that 1% left over, and we get a critical value of 3.250. Now we'll go ahead and plug everything into our equation. So we have our point estimate, x bar 1 minus x bar 2, add and subtract that critical t-score times that standard error, s squared over n for each of those samples. We get a difference, a point estimate of -1, and a margin of error of 4.127, and that gives us an interval from -5.127 to +3.127. Lastly, we interpret that interval. We are 95% confident that the interval from -5.127 to +3.127 captures the true difference in the mean number of chocolate chip cookies, or chocolate chips in Chips Ahoy and Great Value cookies. Note that these sentences always include the word mean. Like in the first two sections, we were always including the word proportion. Another way we can interpret this is that the interval suggests that Chips Ahoy cookies have between 5.127 fewer, that's because it's negative there, and 3.127 more, that's because this one is positive, chocolate chips than Great Value cookies on average. This takes the place of mean. All right, and when we write this out, we write Chips Ahoy in relation to Great Value, because when we calculated this interval, Chips Ahoy was x bar 1 and Great Value was x bar 2. If we're asked if this provides evidence that there's a difference in the mean number of chocolate chips in each of these brands of cookies, we would say no, because 0 is within that interval. 0 would represent there being no difference in the average number of chocolate chips. So since that's in that range of values of our interval, it's possible that there's no difference in the true population means. In our next example, Aaron and Jenna are investigating whether helium balloons deflate faster than air-filled balloons. They have 60 balloons in total. They fill 30 with helium and the other 30 with air. They measure the circumferences at the time of their filling, and then again 3 days later, and they have a mean and a standard deviation for each of these types of balloons. We will make a 95% confidence interval for the true difference in the mean circumference loss of helium and air-filled balloons. We'll start off by defining our parameters for this 95% confidence interval, mu h minus mu a. Mu h is going to represent the true mean circumference loss for helium-filled balloons, and mu a will be the true mean circumference loss for air-filled balloons. The inference method that we have for this problem is a 2-sample t interval. What's changed since the first section is that instead of 2 proportion, we say sample because we're talking about means. And instead of a z interval, this is a t interval, again, because we're working with means. Our randomization condition is met because the balloons were randomly assigned a treatment, either helium or air. And both of these sample sizes are 30, so that's large enough to apply the central limit theorem. Again, our sample sizes are the same. That won't always be the case. If it's not, we'll take the smaller of the two. But for this one, we'll just use that 30 minus 1 gives us 29 degrees of freedom. Go to our table, look up a 95% confidence interval for 29 degrees of freedom, and we get a critical t-score of 2.045. Plug everything in. Here's our point estimate. Here's our margin of error. And we end up with an interval from 23.14 to 25.66. Two different ways of interpreting it. You don't need to know both, but you should understand both. We are 95% confident that the interval from 23.16 to 25.64 captures the true difference in the mean circumference loss for helium-filled and air-filled balloons. Or we could write it as the interval suggests that the helium-filled balloons lose between 23.16 and 25.64 more in circumference than the air-filled balloons on average. Just a couple notes. We're talking about either the difference in the means, or if we're talking about this in the context of the problem, since these are both positive values, the helium balloons are losing more air than the air-filled balloons Again, on average, it's important that we have that there because this problem is about means.